what did we do? We have just, in the previous lecture, right, we just outlined this algorithm quickly over there, but I'm just going to write it carefully and discuss each step in some more detail. Okay, so we first initialize the algorithm with any arbitrary stationary deterministic policy. I'm going to call it by R1, the first policy, which is a candidate for being optimal for the underlying problem. So we will initialize by choosing an arbitrary initial stationary deterministic policy which we will denote by R1, and we will also have just a counter n, and initially we are going to set it to 1. And for each n, as long if we have not stopped yet, if the algorithm has not stopped yet with an optimal solution by the iteration n, then we will have the nth iteration, which, as I said, consists of 2 steps. The first one is the so-called value determination step. Value determination step. Okay. Right? Here, right, for policy Rn, okay, we are going to use all available data, namely one-step transition probability for going from state I to state j under this policy Rn, and immediate expected costs incurred whenever we are in state I under policy Rn. And okay, we will set, first of all, the relative value of the last state for convenience, only for convenience, under policy Rn to 0. We will use all these to solve, okay, the following system of n plus 1 linear equations, linear in the unknowns. Okay, and these equations are just like the one that we wrote before. So we know now that this is long-run expected average cost per time unit if you run Markov chain under policy Rn, which equals immediate expected cost in state I under policy Rn plus, right, we have the sum over all states of the product of one-step transition process from going from I to j under policy Rn times the relative value of state j under policy Rn. Okay, and okay, what is missing over there? The value, relative value of state I under the same policy Rn, right? And we have, as we said, there are n plus 1 equations, one equation for each state between 0 and m. Right? We never forget that we have another equation over there hidden. Right? When you use all of them, we know that now this system has unique solution for, right, all n plus 1 unknowns, which are, right, g of Rn and relative value of state I under policy Rn for each I between 0 and now m minus 1, because we arbitrarily set the relative value of the first state, last state to 0. Okay? So this concludes step 1, the first step. So this way you calculate everything that is relevant to the value of this process, this value of this policy, and then we can move to step 2, which is called the policy improvement step.
Could you explain why we set I to n minus 1?
Because what is missing, it is the Vm of Rn, right? Why we are setting to 0? What was the question? You were asking why we are setting the Vm of Rn to 0 or why? But this is just an arbitrary decision that we make. Actually, when you look at the original equations, we have only n plus 1 equations here, and we need to determine n plus 2 values. So we cannot really solve this system is going to have infinitely many solutions. For each possible value that, for example, this takes, actually you can find values for unique values for others. That means you have infinitely many solutions for this system. But does that really bother us? From the earlier discussion, you may have noticed actually the important quantity for us may be just the difference between these relative values. We are not really interested in the absolute value of any one of these. Because only the difference really gives us actually an idea about how much difference you can expect in average cost or total costs if you decide to start, let's say, in one state rather than the other. Only the differences are important. Right? So you may have actually set this thing to 1 or any other number that you wish. You can still solve these equations uniquely, and then sooner or later you will be actually interested in only the difference. So actually perhaps you can check that if you add any constant c, you will see that all these other values of other values will also be shifted by exactly the same constant c. So no matter what initial value you choose for any one of these relative values, okay, the difference between these relative values will always be the same. And therefore we don't really care which one of these values, relative values, will be set to any arbitrary value, whatever you want. Right? And we just break that arbitrariness by just saying that, okay, we will always assign the relative value of the last state to 0. It's just an arbitrary decision. Okay? But as I said, the only thing, when it comes to the relative values, the values of relative values, we will only be interested in the values relative to each other. Namely, only the differences will become important for us. And for that reason, whether you shift all these values by the same constant back or forth, then will not make any difference for us. And that is basically the reason why we arbitrarily choose one of these values and set it to, rather than an arbitrary value, just to 0. Okay? So I can erase this one, right? Okay. Anything else? Are there any questions about the part we have discussed by now? Okay. Okay, the relative value will show up, I guess, later in our discussion, right? Okay. Even you can see from here, I guess, if you just add c to all of them, right? A constant to all of them, since Pij times c, right, c being constant, the sum is going to be 1, c minus c, they will cancel each other. So you add a c, or if you add c to one of them, you will add c to all of them, then you get another solution. Okay? Alright. Okay. What is going on in policy improvement step? As the purpose of this step was, as I said before, to find a new policy, or just a policy which is at least as good as the original policy for which you determine the values in the first step. Right? And how do you do that? Okay, we use these relative values of relative values of states calculated under the policy at hand, right? So using the current values of Bi of Rn, right? Relative value of state I under policy Rn, computed for policy Rn, right? Our task is to find an alternative policy Rn plus 1. Okay. So what is this? Just let me just be more specific here. So this we know, since we want it to be also a stationary deterministic policy, at every state it is going to prescribe, or we are supposed to describe what the new action that we have to take in each of these n plus 1 states under this new policy. Okay, so our task is what? When we are asked to find an alternative policy Rn plus 1, we have to specify one action that we think we should take in each of these states, in each of these n plus 1 states. While we are doing this, right, find an alternative policy or n plus 1 actions associated with each of these n plus 1 states, such that for any state, at any state I, right, the action k that you choose minimizes, okay, this expression. What is this? This is expected immediate cost we pay in state I because we choose action k, plus the sum as j goes from 0 to m in the state space, one step transition probability of going from I to j under action k, okay, times the relative value of state j into which we just moved, right, according to this probability, under the existing policy Rn minus the relative value of state I, right? So I was fixed, right? Under again the existing policy Rn, all right? So for each, okay, for every state I between 0 and m. Right? So one by one we find all these components of the new policy. How do we do that? When it is the turn of state I, when it is turn of state I, you are looking for some action k, anything between 1 and k, right? That is going to minimize this expression. What is this expression about? Well, you have the immediate cost and one-step transition probability associated with each k, right? But you also use relative values you calculated in the previous step for the existing policy, right? We look at this one, okay? And we choose, for some reason, any one of k's which is going to minimize this. There may be more than one k, but it doesn't matter. You choose one of them, as long as it is it minimizes this quantity. Okay, that's how you find the new policy. In a moment, I am gonna show that the long-run expected average cost per time unit for this new policy is at least as small as the long-run expected average cost per time unit for the policy that we just worked up to this point, right? So Rn plus 1 is at least as good as Rn in the sense that the cost is not going to go up. It may be the same or even better, right? And okay, And if there is at least one case for which this quantity is strictly less than the expected, long-run expected average cost per time unit for the existing policy, then we know that the new policy Rn plus 1 is strictly better. Okay? And as you run this algorithm, if you always, since there are only finitely many possible policies, sooner or later it is going to actually make a dip and it is going to just stay there. Right? And that actually is the reason why this policy, whenever you have finite number of states and finite number of actions, eventually converges in finite number of steps. Not eventually, it's in finite number of steps. Okay? All right. We need to do a small calculation just to support that conclusion. But before that, let me complete this discussion. Right? For any iteration, for any given iteration, n, we first determine the value. Right? Here, in particular, the values that you are really interested in are not really this one, but the relative values, you see. So there are many ways to calculate the long-run average cost. And once you know the policy R, right, you can actually look at the steps transition diagram, set up all those equations for the stationary probability distribution, and multiply stationary probability assigned to state R under policy Rn with the immediate cost you pay in state I under policy Rn, and you can sum all these things to find G. There is even a shorter, perhaps more efficient way to find all these things. And in the meantime, you also find this stationary distribution which can be used for other purposes as well. They provide a lot of information. I guess, and I should say that in step 1, the reason why you are really calculating these things is because you need these relative values in the second step. Right? If you were only interested in long-run expected average cost, then actually there is one way of doing that anyway. So, but when you just look at step 2, the main reason why we are solving these equations is to find these so-called relative values of states. And we need that in order to build actually a new policy which, through this procedure, is guaranteed to be at least as good as the original policy itself. And that's the reason why we call this step as the policy improvement step. So every time you enter to this step, you are going to get out of the step with a policy which is at least as good as the earlier one. And as long as, until you find an optimal policy, the improvement in this step you are going to get is going to be strict. So it is going to be driven to the optimal solution. And as I said before, since we assume that we have finite number of states and finite number of actions, you will have to iterate these two steps on a finite number of times until you find the solution. So therefore this algorithm is quite powerful. Right? It converges, and for reasons that we don't really understand very well, it converges quite fast. It takes, as I said, not more than 15 steps on average, in most cases, before it finds an optimal solution. And after step 2, you have to decide whether you have to actually iterate one more time or whether you have already found an optimal solution. Right? You should be able to, you need a criterion that will help you recognize that the policy that you will have found at the end of step 2 is optimal or not. Right? So that's an optimality test, which is actually quite straightforward. What we do is we just check whether the new policy, Rn plus 1, right, is different or not from the policy just before them. If Rn plus 1 turn out to be identical, and Rn plus 1 and Rn are identical, then right, policy Rn is optimal, and we stop at this point, right? Okay? We'll simply set or reset n to n plus 1 and we perform another iteration. Okay? That's how the algorithm works. Okay. Now, okay, let me now, okay, now this step is called the policy improvement step, and this expression here, quantity, is also sometimes called as a policy improvement quantity. Okay? And the reason is this. Take that quantity, right? Take that quantity where k is basically the variable and just put the state which minimizes that quantity, namely Ci. When you have to replace k, right, with Rn plus 1I is when you are looking at that equation for state I. Then the first term is going to give you the expected immediate cost, right, under this policy Rn plus 1, right, plus, what do you get? You have the sum over all j's between 0 and m of the product, right, the Pij under policy n Rn plus 1 times the relative value of state j under policy Rn. Right? It is Rn. So all I do is I replace each k, these two k's basically, with Rn plus 1 I. Okay? And then there is also this quantities subtracted, right? Vi of Rn. Okay? And by construction, by the way that we choose this quantity, we know that this gives the minimum possible value over all k's, as k changes between 1 and k, of that quantity, which is Cik, right, plus the sum of Pi jk with the relative value of state j minus the relative value of state I, of course under the previous policy, right? So one of these k's is what? Rn of I, right? Rn of I is one of those k's. When I look at the same quantity when k is replaced with Rn of I, right, what I get is going to be something less than or equal to this. Yes, because this is minimum quantity that you can ever achieve. This thing may or may not give that, but in any case you will get a less than or equal to the same quantity if you put this, right? When you put when you substitute Rn of I for k, now this time you get Ci of Rn, the immediate expected cost you pay, right? If you take the action which is prescribed by Rn in state I, plus there is another k here, and that gives you the one-step transition probability of for going from I to j under policy. This time again Rn, right, sum times relative value of j under Rn minus relative value of state I under Rn. We have that. But what is this? Can you recognize this? Now you look at the equation that you need to solve in order to find the relative values. Do they look this similar, or what is missing? This thing, equals what? So you have this part, or even here. Yes, this is G of Rn, which is what? It is nothing but long run expected average cost per time unit for policy Rn. For policy Rn. So this is less than or equal to that. Okay? And this is true for every I. Okay? Now take this inequality, multiply both sides. So left side and right, far right side, okay? They multiply both sides by stationary probability of being in state I under policy Rn plus 1, I guess. Okay? I have one equation for each state I multiply each of them with the corresponding stationary probability under the new policy Rn plus 1, and then sum. Okay, and then sum over I, as I changes between 0 and m. Okay, what do we get? Let's look at here. So you have sum as I changes from 0 to m, pi I under Rn plus 1 times immediate expected cost under policy Rn plus 1, the new policy, plus, okay, I have sum from 0 to m, as I changes from 0 to m, pi I under Rn plus 1 times this sum, which is a sum of, with respect to j, as j changes from 0 to m again, Pij under policy Rn plus 1 times relative value of state j under the old policy Rn. Okay, let me write here, minus, right, sum, the same sum over the same I, as again it changes from 0 to m. I again first multiply with probability Rn, pi I of Rn plus 1. Now this relative value of state I under the old policy. Alright, so what did I do? I multiplied left hand side with pi I Rn plus 1 and then sum over all i's, and then I have to do the same thing to the right hand side. So this quantity is less than or equal to. When you do the same thing, what do you get from the left? You multiply with one probability and then you sum over all probabilities, but the thing that you multiply with doesn't depend on I. So you get the same quantity itself, right? So you still have G of Rn on the right hand side. Okay? Now, why did we do that? See, things will simplify here. The ugliest quantity on the left hand side is this one. Okay? But whenever you see a double sum, you have the habit of just checking at least once what happens when you interchange the order of the summations. Okay? Let's just, here we sum first over I, first over j, and then I. Why don't we just first sum over I and then j? So look at that double sum first. So double sum on the left hand side becomes what? Becomes, after we interchange the order of summation, namely first I sum now over j, as j changes from 0 to m. Well, if j goes out, see, Vj of Rn, we can take this also outside just before the next sum, because it doesn't depend on R. So I can just write Vj of Rn first, and then sum over now over I as I changes from 0 to m. What is left? I have, well, this depends on I, so it should remain inside the second sum, right? Multiplied with Pij under policy Rn plus 1, right? Okay, I'm looking at this one. And what do you think this gives you? Pi I times Pij's? Pi j. That's true. This is pi j under policy Rn plus 1. Exactly. So now this simplified. Now instead of a double sum, you in fact have not a double sum, but just a single sum where you have, okay, let me write this first. Pi j, right, under R, the new policy, and the relative value of state j under the old policy. Now let us take this and put it back here. What happens to the left-hand side? Now left-hand side, you had a sum. Well, actually, maybe I shouldn't do that. Right? We can see what happens. Okay, this thing is given now by this. But there is another term on the left-hand side which is exactly the same with a minus sign. So in fact now we know that these two terms just cancel each other. Right? So on the left-hand side, what you have is the first sum far on the left, right? As I changes from 0 to m, you have stationary probability of state I under new policy Rn plus 1 times immediate expected cost incurred in the same state I, again under the new policy, less than or equal to long run expected average cost per time unit for the old policy. Well, what is this sum? What is this? Does this have a name? So what is that? G R or what is it in English? This is the long run expected average cost per time unit under the new policy, right? And what did we learn? It cannot be more than the long run expected average cost under the old policy. And so now this just proves what? Every time you run step 2, the new policy you obtain from the old policy is going to be at least as good as the old policy. It is at least as good as old policy because this inequality may actually hold with an equality. Right? But you see that if for one of the states I, only one is enough. If for one of the states I, if this is like this, for 1, right? When you multiply with the pi I of Rn plus 1 as before and the sum them all, then you still have a strict inequality here, right? And therefore you will have a strict inequality here and strict inequality here, right? So that means what? If for at least one of the states you find an action that gives a strictless, an action that gives or that makes this inequality strict, then you are actually improving the previous policy by a new one in a strict sense. Okay? So that's also important. But okay. Now, all right. So I guess I told everything that, at least for this course, that you should know about this algorithm. Perhaps we should actually go quickly through an example to see how you can actually use this. Right? Are there any questions? Do we have any questions about the calculations we made here? Right? Okay, you remember this maintenance problem that we discussed while we are talking about the linear programming formulation for the same problem. Why don't we look at the same problem and now try to solve it by using policy improvement algorithm? Right? So let's try to solve the maintenance problem. By using policy improvement algorithm. So you may not remember what this was about, but I can at least give the decisions and states, and as I'm describing them, in the meantime, we'll also remember the problem itself. So 3 types of decision can be made. Either you just do nothing, right? Or you overhaul this machine, or you replace it, right? You remember that there was a crucial machine that is key for the production, and every week we just inspect its status. It can be in one of 4 states. Either it is good as new, or it is operable with minor deterioration, or it is operable with major deterioration, or it is inoperable. 4 states, from 0 to 3. And in each of these states, we have 3 decisions in principle that we can take, right? Either we do nothing, we just let it go as it is for at least one more period, or we just overhaul that corresponds to a limited repair, and we remember that it was effective only in state 2. It just doesn't do anything infeasible in the first place if the machine is inoperable, and if it is good as new or has only minor deterioration, it doesn't. The overhauling doesn't is not effective, and it was only useful for state 2 when the state is inoperable with major deterioration. Right? So just observing all these constraints, we know that for each of the following states, we can make one of these decisions, and for each of these combinations, we also know the cost figures. And they were like, okay, we can make, for example, decision 1, which corresponds to do nothing, only in states 0, 1, or 2. So this was good as new state. Okay, this was operable with minor deterioration, and state 2 was again operable state. The machine is operable if it is in this state with major deterioration. Okay, and finally state 3, which corresponds to the state of machine in an inoperable state of the machine. All right, and we have the costs, right? And if you do nothing, and if the machine is good as new, there is no cost associated with it, right? And if the machine is operable with minor deterioration, then you pay for the cost of defective production, which was about $1,000. And if it is operable but with major deterioration, the cost was $3,000. And if it is inoperable, then this is, okay. So this is not allowed actually, right? Now I remembered, right? So since the production should go forward, if the machine is in state 3, do you remember that? You are required to replace the machine, and the machine should, because the production should go forward. Okay. So in the decision 1 is allowable only in those 3 states. Decision 2, which corresponds to overhauling the machine. I talked a lot more about this, explain that it is allowable only in state 2, and the cost was around $4,000, right? $2,000 was for just performing this overhauling, and then there was also $2,000 production loss because overhauling the machine takes about a week. And there is also decision 3 that you can choose, which corresponds to replacing the machine itself, and this is allowable. You can take this action, or it makes take this action only in stage 1, 2, or 3, not in stage 0, because in stage 0 machine is good as new. There is no reason to replace it in stage 3, and the cost was $6,000, right? $4,000 was for replacing, or the price of a new machine, and it takes a week to replace the machine, so you also accountable for the $2,000 of production loss, right? So having all these cost figures, now we can use policy improvement algorithm to solve the problem. The algorithm is over there. The first thing that we do is what? We initialize the algorithm. We set our counter to 1, and we choose arbitrarily one policy. Okay? And this can be the policy which says we do nothing in stage 0, 1, or 2, but we have to replace, right? When the machine is in state 3. Okay? Let's start with this one. Okay? So do nothing in states 0, 1, 2, and replace the machine if it fails. If it is in state, okay, if it is in state 3. Okay? Alright? And let me just summarize what the costs and decisions and all relevant or important information that we will need to use in the next step about this policy R1. Okay? So for in each state I, so it is already there actually, right? So for each state 0, 1, 2, or 3, under this policy R1 we make decisions respectively do nothing, do nothing, do nothing, and replace, and most importantly the costs. The immediate costs we incur when we are in any one of these states, and then follow the corresponding decision, right? If you do nothing when the machine is good as new, you pay nothing. If you do nothing when this machine is in state 1, then you pay 1,000 per week, right? And when it is in state 2, you pay now 3,000 per week for the cost of defective items as before. And now in state 3, since you must replace, then you pay $6,000, right? So we have all these things. Now the algorithm, now we have to just do the first iteration, right, of policy improvement algorithm. There are 2 parts that we have to do. In step 1, we have to determine the value of this policy, value determination, right? And then we will use the results, and here we will find the relative values of this policy, and then we will use them to find a better algorithm in the so-called policy improvement step, in second step, right? So let me stop here and give a 10-minute break, because this is going to take a while, right? So we better not split our time. Okay.